Welcome to today's class. The topic of today's lecture is elastic constants. Under this topic, we will learn various types of elastic constants. Like the first one is the modulus of elasticity, also known as Young's modulus and denoted by capital E. The second one is bulk modulus, generally denoted by capital K. And the third one is the modulus of rigidity or shear modulus, generally denoted by capital G or also capital M or C at various occasions. Now we'll discuss each one of these three one by one. The first one is elastic modulus. Elastic modulus is basically capital E, that is a ratio of direct stress by linear strain or longitudinal strain. We generally denote this one by sigma divided by epsilon, and if we put up the expanded form of sigma, that is equal to P by A and epsilon is delta L. So rearranging this ratio, it comes capital P into L divided by A and delta L, that is the change in length. So this is PL divided by A delta L. Its unit is generally Newton per millimeter square or Newton per meter square, but the Newton per millimeter square is also popularly known as megapascal, that is MPa. So if we go in detail, a graphical representation of the stress strain curve of a ductile material, you can see the graphical plot comes like this, in which the origin, you can see here, from origin up to some distance, a straight line plot is there. It means that the stress is directly proportional to strain, and the slope of this portion, the straight portion of the plot, is constant. So this slope is basically governed by the Hooke's law, that is within elastic limit, the stress is directly proportional to a strain. It means that within this plot, if we release the load causing the strain, then the material strain is, deformation is recovered back. Material comes back to its initial stage, and this way it performs as a purely elastic material. But if the load exceeds the elastic limit, then the nature of the curve becomes non-linear and it enters into the strain hardening zone, and the latter it becomes the necking zone, when the material becomes thinner and thinner, and at one ultimate load it extends further, and at a fracture point the material breaks. So for a ductile material like a low carbon steel, this type of stress strain curve is popular, and the Hooke's law is only valid up to the straight line portion of this plot, starting from the origin up to some value of stress. So this is worth remembering. Everybody should know that what is the stress strain curve for a low carbon steel. If you understand it better in some more point-wise description of this plot, you can see that in this plot the origin is here, that is the marked by O, 0. Starting from O to A, the plot is horizontal, straight line, and this straight line plot is as per the Hooke's law. If the load exceeds further, then this curve becomes non-linear. The last point up to which this plot is linear is known as proportional limit, and up to some further points when the load exceeds, then it becomes the elastic limit or yield point B. Beyond B, the material enters into the plastic zone, and after C, it behaves in a plastic manner. So the plastic behavior starts from this. After C, the material is no more elastic and it enters the plastic zone. Plastic zone means without substantial increase in the stress or load applied, the speed of increase in strain is very high, and this is the flow nature of the material, and finally it reaches up to a point of ultimate load, and beyond that it starts flowing without any increase in load. So the stress tension curve of a low carbon steel and ductile material gives us a very clear picture of the Young's modulus of elasticity, that is the slope of the straight portion of this stress strain plot in case of a material. Now, as we know that the Young's modulus is the ratio of stress and strain, now to learn about its application, we are going to solve a numerical problem. The numerical problem is that suppose a wire 2 meter long and 2 millimeter in diameter, when stressed by a weight of 8 kilogram, has its length increased by 0.24 millimeter. So the load applies 8 kilogram over this wire, and it is stressed by a length of 0.24 millimeter beyond its initial length, that is 2 meter. Find the stress, strain and Young's modulus of the material of the wire. Take G, the acceleration due to gravity, equal to 9.8 meter per second square. Now, to begin with the solution, you can see the stress would be equal to P by A, the force divided by the cross-sectional area, and this is P is 8 kilogram weight, so the force corresponding to this mass is m times G, and this is mg, the P value, divided by the cross-sectional area of this circular wire. So this is pi r square. Since the diameter is 2 millimeter, so its radius is 1 millimeter. So taking here the data, so this is 8 kilogram multiplied by 9.8 G divided by pi 3.14 multiplied by this 1, that is 1 millimeter means 1 into 10 to the power minus 3 in meter, and to the power 2, it is r square, and by calculating this it comes 2.5 into 10 to the power 7 Newton per millimeter square. So this is the value of stress in this question. Now strain is basically delta L by L, as it is given in this problem that the length is increased by 0.24 millimeter. So the delta L is 0.24 millimeter divided by the total length, initial total length, that is 2 meter, basically 2 into 1000 millimeter. So this comes 0.12 into 10 to the power minus 3, that is 1.2 into 10 to the power minus 4. So this is the value of strain. Now to calculate the Young's modulus, that is denoted by capital Y also, or capital E, is equal to stress by strain. So taking this two value of stress, that is 2.5 into 10 to the power 7 divided by 1.2 into 10 to the minus 4, and it comes 2.08 into 10 to the 11 Newton per millimeter square. So by this way, by applying the formula for Young's modulus of elasticity for this given data, we have calculated its value. Now we will go to another elastic constant, that is bulk modulus K. So the K is basically the ratio of the pressure applied divided by the volumetric strain, that is pressure, that is a stress like parameter, divided by the volumetric strain, that is delta V by V, change in volume divided by initial volume. So where delta P is pressure applied on all surfaces of a body, and because of the entire surface is applied by some pressure, so the whole body will change its shape because of under the influence of this pressure. So the effect of the bulk modulus is visible over the entire body, and if we calculate the delta V, that is change in volume, is due to the applied pressure only. So this is valid for any type of material, either solid or liquid or gas, because in case of any material, the entire material can be applied, can be kept under some pressure, and that pressure applied can result into some volume change. So by this equation we can find out bulk modulus. To better understand this bulk modulus, one problem has been taken, and what is the bulk modulus of a body that experienced a change of pressure of 5 into 10 to the 4 Newton per meter square, and its volume goes from 4 cm cube to 3.9 cm cube. 4 cc to 3.9 cc. So another solution, you can see the bulk modulus basically K is delta P divided by the volumetric strain delta V by V. So here K is directly equal to the delta P, the pressure applied. Pressure applied is 5 into 10 to the power 4 Newton per meter square. And the delta V, that is the volume change, delta V is 4 cc minus 3.9 cc divided by the initial volume, that is 4 cc. So by taking the values, we get K equal to 0.125 into 10 to the 4 Newton per meter square, or we can rewrite it, that is K becomes 1.24 into 10 to the power 5 Newton per millimeter square. So this way we can solve it and we can find out the bulk modulus of a material. Now the third elastic constant is the modulus of rigidity, that is capital G, and this is defined as the ratio of the shear stress applied upon a surface divided by the shear strain. Shear stress is basically the shear force divided by the shear surface area. So the shear force is applied to some parallel to some surface. So if you know the surface area of that surface, if you know the area of that surface and we get a ratio like this, then we can get the value of modulus of rigidity. So the surface area is the sheared surface area parallel to the shear force. So if the shear force is Q applied parallel to the surface and that area of that surface is capital A, then this shear stress will be Q by A. Now shear strain is basically the shear displacement divided by the original length. So to further understand this, if we take a numerical, suppose a 5 centimeter cube of substance and its upper face displaced by 0.65 centimeter by a tangential force of 0.25 Newton. The tangential means the force is applied parallel to the surface. Calculate the modulus of rigidity of the substance. As per formula, we write modulus of rigidity equal to capital G, and this capital G is shear stress, that is Q by A, divided by shear strain, that is the delta by H, the shear deformation in the direction of the surface, in the direction of the force is delta, and the dimension which is deformed is H, so delta by H. So if we rearrange this, becomes QH by A delta. Now putting all the values here, the Q is given 0.25 Newton multiplied by H, that is given here 5 centimeter, that is 5 into 10 to the minus 2 meter, divided by A, since it is cube, so its area is 5 into 5 and into 10 to the minus 4 meter, into delta, the displacement in the direction of shear force is 6.5 centimeter, 0.65 centimeter, that becomes, this is 6.5 into 10 to the minus 3 meter, and if you calculate this, it becomes 769 Newton per meter square. So by putting all the values in the basic definition of modulus of rigidity, we can get its value. Now the interrelation between these three elastic constants are also important to know. The first relation you can write the Young's modulus of elasticity E equal to 2 times G, that is modulus of rigidity, multiplied by 1 plus mu, that is Poisson's ratio. So E equal to 2G bracket 1 plus mu. Now another equation can be the E equal to 3K, K the bulk modulus, multiplied by 1 minus 2 mu, the Poisson's ratio. So by using these two equations, we can calculate any value of elastic constant if the other values are known. Here in this equation, if we know the value of rigidity, modulus of rigidity, capital G, we can find out E. Or if we know the value of bulk modulus, we can also find E, and vice versa. Similarly, if we know the value of G, we can find the value of K by equating these two equations. So this way we can work with the elastic constants and solve some numericals which is related to these three elastic constants. With this, thank you very much.